let's be honest. For guitarists, pickups are kind of like shoes for the fashionista. We're always trying to pair the right pickup with the particular instrument and the genre, kind of like trying to pick the right pair of shoes to go with the right outfit for a particular event. There are all kinds of different pickups. There are single coils. There's different kinds of single coils. There's humbuckers. There's the lace alumitone. There's gold foils. There are so many different kinds, but a lot of times it boils down to trying to find one that sounds the way that we want it to sound for our particular instrument. Now, there have been some really cool developments in the commercial pickup world with things like the Fishman Fluence pickup system, which allow you to have different voicings for the particular pickup. And if you go watch the video that Fishman did about the construction of it and everything, it's really quite cool. But those Fishman pickups, as awesome as they are still pretty expensive, and you only get 2 or 3 different voicings out of each pickup. But what if I told you that there was a pickup that you can build on your own that will allow you to infinitely tune the sound of your pickup to whatever it is you want? And in fact, you could even set it up so that you could change those voicings on the fly. That's what I'm going to be talking about today, is a DIY pickup system that uses parts that you can source online pretty easily with a simple circuit that will allow you to dial in the pickup sound exactly the way you want it. You can make it sound like a big fat overwound humbucker, or you can make it sound like a super thin low wind single coil to anything in between. So stick around and I'll talk about not only how to do it, but the whys as well. So here I'm using LT Spice, which is a circuit simulator, and in this simulation I have got 4 different pickups that I've simulated that are representative of the most common types of pickups out there. And let's just look at one of these. This is for a regular PAF style humbucker here. And the representation for our pickup is that, being a coil of wire, it not only has the resistance value, which is what we're very used to seeing in all of the specifications and advertising literature, but it also has an inductance, and it has a small amount of capacitance that occurs from having all of those windings of wire so close together. So this section right here, L1, R1, C1, are the pickup itself, but I've also put in our volume potentiometer, which right now this is volume is on full, and then our tone potentiometer with our tone capacitor. And right now, with the way that it's set up, is that the tone is all the way up. And then we have a small amount of capacitance for our cable, and then the input impedance of our amplifier input or a pedal input right here. And because we are never just taking the pickup itself, there's always something else associated with it, you know, at the very least, a cable and the input to a pedal or an amplifier, even if we don't have the onboard guitar controls. But I've simulated all of this here, and I've done it for 4 different pickups. We have a humbucker, we have an overwound humbucker, we have a single coil pickup, a Strat style single coil pickup, and an overwound Strat style single coil pickup. And the thing that is different here is the inductance and the resistance of each of the pickups. The inherent capacitance in each of these is all basically the same, and that actually comes from measurements that some very dedicated people online have taken of pickups and found that nominally between 100 and 130 picofarads is the typical capacitance of a pickup, whether it is a humbucker or a single coil. But as you can see, this humbucker is a PAF style humbucker, and it has an inductance of about 4 henries. That inductance is not just the coil, but also the pole pieces that run through the center of the coil. They help augment that inductance. And then we have our DC resistance here. And so this is characteristic of a typical PAF pickup. This overwound pickup actually has the specifications for a Seymour Duncan JB style pickup. The single coil pickup has an inductance of 2 henries and a nominal DC resistance of 6 kiloohms, which is fairly typical of a vintage spec Strat style single coil pickup. But then if we were to go to an overwound style Strat single coil pickup, that inductance can get up to about 3 henries and, 8.5, sometimes even 9 kiloohms. And so what I've done is I've actually simulated the AC response for each of these 4 pickups here. And the thing to note here is that each of these responses is pretty flat through the low frequencies, but starting above about 1 kilohertz, it starts to rise until we hit a resonant frequency. Because of the inductor and the capacitor in our equivalent circuit here, this creates a resonant second order low pass filter topology, which means that there is a point where the circuit hits a resonance, and above that resonance, it rolls off at about 12 dB per octave. And so if we look at our 4 curves here, this yellow curve here is our overwound humbucker, which has the smallest rise in its resonance and the lowest frequency at which that occurs. That's because the inductance is so high that it has pushed that resonant frequency down. And because there's so much DC resistance here, it actually takes that resonant peak and it kind of smushes it out. It doesn't allow for a really sharp peak to develop. And then this blue curve here is our regular humbucker. The red curve is our overwound single coil. Sorry, this is the overwound single coil. And then this final curve is for our vintage single coil pickup. And you'll notice that it has the lowest resistance and inductance, which means that the resonant frequency gets pushed way up and its resonant peak reaches a higher amplitude and has a sharper Q factor to it. Okay? And so these plots actually describe a lot of what it is that we hear as the differences between pickups. Okay? We talk about how a vintage style Strat pickup is really clean and has lots of treble and is, we may use terms like jangly or chimey or whatever it may be. And it's that we're hearing lots of this upper frequency content where the human ear is really sensitive, and we perceive that content as being jangly or chimey or having a lot of high frequency bite or whatever it is. And down here, with an overwound humbucker, we actually are rolling off a lot more of the highs. There isn't that really sharp resonant response. And so we perceive the output to be mellower. Now, the one thing that the simulation is not showing is the actual difference in absolute voltage. Okay, this is just a normalized response. A normalized frequency response, just so that we can compare these resonant characteristics across each of them. So when we're cycling through all of these different pickups, what we're really doing is we're going through trying to find a combination of resonant frequency, the Q of that resonant peak, and the cutoff frequency of that resonant peak. So we can think of it as essentially trying to choose a parametric a single band parametric EQ that is pleasing to us to work with the instrument and to work with our amplifier and everything. So if we want to make a pickup that will allow us to get any of these voicings, then one thing we can do is to first create a coil that is not going to get rid of any of this high frequency information. If we can start with a coil that is going to be super, super flat, then we can use active electronics to boost the region that we're interested in and roll off the high frequencies above that region. So I've actually here got simulated a coil that has very low inductance, so 0.1 henries, and only 2 ohms, and a very small amount of capacitance because we're using very little wire. And then we still have, we've got the other components here, but I've set them to really high values because what we end up having to do with this is we end up having to buffer it, which I will talk about later. But these measurements for these parameters here actually are the parameters for the tunable pickup that we're going to see a little later in this video. And so if we were to look at the response here, we get this purple line that is really, really flat. You can see that going all the way up to 10 kilohertz, we get a change of, something around 1 dB. So very, very little change in response. So what this does is it gives us a clean palette to start with. In fact, if you were to hear just this coil without any kind of filtering on it, it sounds pretty harsh because there's so much higher frequency content up here that other pickups don't reproduce. But this allows us to be able to apply filters to it so that we can recreate any of these responses that we want, and even ones in between, so that we can create anything from a tonality of the most overwound humbucker all the way up to the most pristine, almost ice picky single coil pickup. Okay, so that is what we're going to be shooting for. And then what we will do is we'll pair that with some active electronics to do the filtering. One of the benefits of doing this as well is that we can also start introducing different equalization for things that we can't even achieve physically if we wanted to, or we can do things where we can introduce more advanced filtering to make it sound more like an acoustic guitar, for example. And that's going to be a little bit outside of the scope of what I'm going to be talking about here, but it is certainly possible to do that. So if we take a look at these curves, we have already discussed how it's as if we have some kind of a parametric peak here and then a low pass filter above that peak. And so now what I'm going to show you is a schematic that I came up with for a circuit that takes the input from a very low inductance, low resistance coil, which is going to have a really wide bandwidth, and allows us to filter it in such a way that we can get a really wide variety of tones out of it. So this particular circuit is actually pretty straightforward. It's 4 op-amp stages. This first op-amp stage here is just a unity gain buffer. And that buffer is used to provide a high input impedance so that we can take the output from our coil and not have any losses or very little losses by virtue of buffering the signal. And then what we do with this second op-amp stage here is this is actually a second order Salin key low pass filter. So this is going to provide that 12 dB per octave roll off that we want. And this potentiometer right here is going to set where that frequency is. The values that I've chosen here will give us a corner frequency between about 2 kilohertz and 4.5 or 5 kilohertz, which covers kind of that whole range from overwound humbucker all the way to underwound single coil pickup. And if you want to learn more about the Sallen-Key filter topology, there's lots of good articles online that you can go read about. Next up is we're actually using these final two op-amp stages to create a fully parametric single band fully parametric equalizer here. So we have a potentiometer that is going to control the gain of our peak or the amplitude of our resonant peak. And then using a gyrator or a simulated inductor here, we can set the Q of that with this potentiometer, which is how wide our resonant peak is. And then we can also set the frequency of that resonant peak as well. And so that allows us to move that resonant peak up really, really high if we want a really kind of sparkly, clean tone. Or we can move it way down to, around the 2 kilohertz range to be much more like a very overwound humbucker. And then on the output of that parametric equalizer, we just have this output capacitor, which is going to block DC voltage out. And then we have a volume potentiometer. And the only other thing that we have here is a reference voltage that we use for biasing our op-amp stages so that we can make sure that we get enough signal swing. Now, another thing to note is that this is maybe a little more complex than is necessary to achieve what we need, because I mentioned that the response of the pickup looks very much like a resonant low-pass filter. Well, you can actually achieve a resonant low-pass filter using a single op-amp stage. So you could have a buffer and a resonant low-pass filter. The only issue there is that with that resonant low-pass filter, it can be a lot harder to dial in exactly the cutoff frequencies and the Q and the gain of that resonant peak. There's a very narrow operating range for resistances to allow you to do that. It's certainly possible, and I actually have another circuit that I'm experimenting with right now that will allow me to use just my same 4 op amps, but will allow me to get 2 or 3 different voicings from a single quad op amp package here. But this is really all that we need to do, where, for example, if we wanted something to sound like an overwound single coil, for example, we would have our low-pass filter be a little bit less than our maximum cutoff frequency. We would have our gain set somewhere maybe like 50% perhaps. The Q would be less than maximum, probably somewhere around the 50 to 60% mark. And the frequency would be at around the 3/4 mark. And what that would do is that would essentially mimic this red line that we have here, where we don't have quite as much resonant peak gain as a regular single coil, and we're not quite as high in frequency, but we have a much higher low-pass filter cutoff than either of the humbuckers here. And so we could use that to create kind of this sort of response, and there'll be some sound samples a little later about that. So I mentioned how this pickup is easy to build on your own, and I wanted to show you just what exactly goes into building the pickup itself, and it is really quite simple. As we all know, a pickup is just a coil of wire around some magnets, and this pickup is actually going to be really just the same thing. So this particular design is going to use 2 coils of wire, and I've got these coils here. They have some metal slugs here in the middle that are this is just mild steel that is made to fit inside of this bobbin. And I have wound this with some wire that is significantly thicker than typical pickup wire. Typical pickup wire is around 42 gauge magnet wire, but this here is 28 gauge magnet wire, which is significantly thicker. You can see that you can actually see it. For one, it's not like the thickness of a human hair. The thing about thicker gauge wire is that it also has less resistance per meter, meaning that we will have less of that series resistance from our schematic that is going to make it so that we don't have quite so much of the damping due to the resistance. So that means it's going to preserve more of those high frequencies that we need in order to be able to shape it to what we want. And so we have two coils here, and these coils get attached to a base plate, and I've got two different styles of base plate that I've made. One is single coil and one is humbucker sized. There's no real difference between these. It's simply form factor for what fits in the routing of your guitar or your pick guard. I have used both. I tend to use the humbucker sized one just because I tend to route humbucker cavities more than I route single coil, but inside they're both exactly the same. And you see that I've got these white rectangles that I've put on my base plates, and that's for my magnets. Now these magnets are not typical pickup magnets. These are neodymium magnets. The ones that I have here are 1/2 inch by 1 inch by an 1/8 inch thick, N52. That's the grade of the magnet. You want the really strong magnet because that's going to create a stronger magnetic field, which means that you will be able to get a stronger signal. And the way that we're going to assemble all of this is that we are going to do reversed wound, reverse polarity of these two coils, but they're going to be wired in parallel. If you've ever wired a humbucker in parallel as opposed to in series, you will have heard that instead of having that really big full sound that we're used to with a humbucker, it's a little bit of a thinner sound. And that's because it's keeping more of those high frequencies because you are actually reducing the overall the overall inductance and resistance of the pickup, because resistances in parallel divide each other as opposed to adding together in series. So in order to make sure that our magnets are opposite polarity, we just make sure that they stick together. Okay? And I actually have a pair of videos for assembling these as a sustainer driver that goes into a whole lot more depth, and I will link those in the description. But we make sure that they stick together on the side because these neodymium magnets are magnetized through their face as opposed to a typical guitar magnet, which is magnetized through its edge. And we glue these down onto the base plate inside those rectangles. Do it one at a time so that they don't snap together, but you glue them down with super glue until they're all set and everything, and then they won't slide together and stick like that. And then you put the coils on top of the magnets, and it's simply a matter of feeding the wires of the coils into the base plate and soldering them, because if you take two coils wound the same way and you wire the starts and the ends together the way that this base plate is, that means that it'll put it in parallel and they're connected to the pads for our lead wire. So, your stack up in the end. Whoops, bumped the camera. Stack up in the end will look something like this, okay? And then you just put a cover over the top of these. You'll see in the demo that's upcoming that the cover that I have made has these slanted pieces of steel that go over the top of these slugs, and that just helps bridge the magnetic gap that's going to exist between these two slugs here, so that you don't get a dip in output signal strength when you bend your strings, or if you have an odd number of strings or what have you. But the coils and the base plate are only part of the equation, because you'll remember that these are very low wind and low inductance and low resistance, which means it's going to be very low output. But what we're going to do is we're going to use a transformer to step that signal up. Now, the reason we use a transformer is because the voltage gain that you can get out of a transformer can be very, very clean if you use a good transformer. And that means that instead of doing all of the gain with active electronics, where we would be amplifying any kind of thermal noise in our components, or having to use several stages to boost it up, we can use just a single transformer. Now, this transformer here is I think this is just a Zycon transformer that I got from Mouser. The thing that you want to look for in a transformer is a high winding ratio, where one side is very, very low and the other is really high. So this has an 8 ohm primary, and it has, I think it's either 1200 or 1500 ohms on the secondary. And the way that transformers work is that your voltage gain goes as the, I think it's that it goes as the square root of the winding ratio, which I'll have to look that up. I don't remember offhand. But when you have the secondary have a lot more winds than the primary, that means you're going to step up your voltage a lot more. Okay? Now, while this transformer works, there are a couple things about transformers that I just want to mention. And one is that if you go with a really cheap transformer, then the core material in there, that's my soldering iron beeping, the core material can saturate, and it can introduce distortions that we really don't want. And the other comes down to size. While this is a relatively compact transformer, it's not all that big, there is another transformer that I greatly prefer that is significantly smaller. You can see how small this guy is compared to the other one. This is a triad transformer. It's a military spec audio transformer that has the same winding ratio and same impedances as this Zycon one, but it has been made in a much smaller, much more robust package here. Now, with that comes a big difference in cost. This one was $3 or $4, I think, the Zycon one, and the Triad one is about $18. However, the cost of the magnets, depending on where you get them, is $1 or $2 a piece. The bobbins can be 3D printed. The wire is relatively inexpensive, like all magnet wire. You can get just, because we're not using very much, you can just get like a little 4-ounce spool of wire, and then this is just 1018 mild steel in here that I cut down to fit inside the bobbin. And so the cost altogether, including the $18 transformer for all of this, is really only about $25 per pickup. I'm not going to get into all the finer details of the construction of it. The other videos that I'll link to really get into that, but I wanted to show you the pieces of what go into this. So there we go. Hopefully you found that useful and enjoyable, and hopefully you have seen just how easy it can be to make your own pickup that will allow you to get a really wide range of sounds without having to go through the hassle of pulling out pickups and rewiring them and everything over and over. If you are interested in making one for yourself, I have put a link below to all of the files that include the bobbin files and the schematics and everything else that you're going to need to be able to put one of these together for yourself. So have at it, take care, and we'll see you next time.